Our next assumption is that all variables are measured without error. Now remember that measurement error and prediction error are two different things. There's always going to be prediction error. We're not assuming away prediction error, but we are assuming away measurement error. Now, here's how this works. Measurement error goes like this. Someone's score on a particular variable is a sum of two things. Their true score plus measurement error. So your true score is how you actually are on a particular variable. Our observed score, that's what the O stands for here, observed score is the sum of the true score plus a measurement error. That's classic test theory. So observed score is equal to true score plus measurement error. And measurement error is just about the unreliability of our measures, that somehow our measure of a thing is going to be different than the actual thing that we have. And there's always going to be, or almost always going to be, some sort of measurement error. Our goal is to reduce it. Now, measurement error can come from two sources. It can be random error or non-random error. Random error is error that's unrelated to your true score. Non-random error is error that's related to your level of a true score. So what do I mean by that? Say we're giving a test about, or a survey about conscientiousness, and we ask people, how do you rate yourself on conscientiousness? Well, we would expect that people who are very conscientious would probably say, you know, I'm very good on this, I want to make sure I get this exactly right, I'm probably not in the extremes, I'm probably somewhere in the center. On the other hand, someone who's not very conscientious is going to say, oh yeah, I'm great. Right? I know that I get hired based on conscientiousness, so I'm going to make sure that I just make it high. I'm not going to be very conscientious about my response. So the level that your actual level, your true score of conscientiousness, has an effect on how you answer. Therefore, the measurement errors are related to that true score, and so it's non-random. Another example is leniency bias. Right? So some raters will look at people who are poor performers and give them the benefit of the doubt and give them a higher score than they otherwise deserve, but don't give that same leniency to people who score higher or average on that. So that's a leniency error, a leniency bias, in which the error, the measurement error, is related to someone's true score. Same thing with the halo effect. Sometimes we rate people who we see as rating high in their performance, we rate them even higher than they otherwise deserve. Whereas people who are of average or low performance, we rate them either the amount they deserve or even possibly lower than they deserve. Therefore, the observed score, the one that we actually score, includes both their true score and a non-random error that's related to their true score. So, look, obviously that's a problem, and we'll talk about this. There's now the other kind of error is so that's non-random error. The other kind of error, measurement error, is random error, and that's basically about reliability. If we have an unreliable measure, it introduces random error into it. Error that's not related to their actual measure of a true score, error that's just randomly assigned or randomly involved because of just the way that we measure things. So there are ways to correct for this random error. We can correct factor by correlation. If we look at the row, so this is kind of our true correlation, it's going to be equal to the correlation between x and y divided by the square root of the reliability of x, times the reliability of y. Right? So in other words, we need to correct our observed correlation between x and y by the reliability of x, the reliability of x and reliability of y. And that's going to give us our true population correlation. We don't typically do this, but in areas like meta-analyses and some other areas, we may make this correction. So here's the thing though, we violate this assumption all the time. There is almost always measurement error. And so the question is, what do we do about it? Well, the first piece is random error. How do we deal with random error? If we have random error in the dependent variable, the y, it kind of doesn't matter. Our results will not be biased. So we can just ignore that. If, on the other hand, we have random error in our measurement of x, the independent variable or the predictor variable, that can cause problems. The problem it creates is that any correlation or regression coefficient that relates this unreliably measured variable to an outcome variable, those correlations are going to be artificially low. In other words, it biases these results towards zero. So the correlation between an imperfectly measured predictor variable and a perfectly or imperfectly predicted measured outcome variable is going to be biased towards zero. What this means in practice is that our estimates are actually a little bit more conservative than is true in the real world. So what does this mean? One, if we find a significant result, so if we have a significant correlation or a significant regression coefficient, and there is measurement error, that's okay. That just means that the bias would suggest that that is actually truly significant. If anything, if we got rid of the bias due to measurement error, that would be an even stronger relationship. So we can generally ignore it and say this is just a conservative outcome. If, however, we don't get a significance, right? We don't get a significant correlation or a significant regression coefficient, we might be concerned. We might not want to just throw that away and say, well, I guess there's no relationship. We might want to go back and look, is this possibly due to measurement error? Because measurement error is going to make our tests less powerful. It makes them more conservative. It makes it harder to detect. That's one of the reasons we want to get rid of measurement error, so that we can actually detect things that are there. So the bottom line is we could ignore measurement error pretty much in the outcome variable. In the predictor variable, measurement error, the random measurement error, is due to, or it causes us to be more conservative in our estimates. So we know that if we find something significant, we're just conservative in our estimation of significance. If we don't find something significant, one place that we can look is measurement error as a possible reason why we don't have a significant result or a significant relationship. Now, non-random error, that's a problem. Whether that happens in the IV or the DV, non-random error is always a problem. The problem is that it biases our relationships, and it biases it in unpredictable ways. Whereas random error in the IV biases our relationships in a predictable way, and it biases them towards zero. Non-random error, whether it occurs in the outcome variable or the IV, is unpredictable. We don't know how it's biasing them, so that can be a problem. Now, in general, we tend to ignore this as an issue. Other than to say, we try to reduce our errors as much as we can. We try to make sure that we have good variables. We employ or we become psychometricians to make sure that our measures are as reliable and as valid as they possibly can be. So maybe some things that we don't do or things that we consider is look out for social desirability, right? Where we ask people or we tell people, hey, conscientiousness really affects this test, or tests whether or not we're going to hire you. Are you conscientious, right? Or we ask people, are you an honest person? In which case they're more likely to say the people who are honest are going to say yes. The people who aren't honest are going to say yes because of that social desirability bias. We need to be aware of rater biases. People who are lenient, overly lenient, or have too much of a halo effect. This reduces the reliability of our measures and can increase non-random error. We can watch out for central tendency bias, where people tend to rate in a 5-point scale, they'll rate the 2, 3, and 4 much more often than they'll rate the 1 and 5. This introduces non-random error. Now again, the bottom line here is make sure that you have good measures. Make sure that they're reliable and valid, because when they're not, we're violating a regression assumption, which means that we have to be very careful about how we interpret our results.